Welcome to lesson 2 of our fault calculations module. And in this lesson, we are going to be looking at your sequence networks, how they act on three-phase networks. So we are firstly going to look if we have got loads into our system. And the first part is your star connected loads. So the figure you see on my left hand side is showing that I've got a star impedance load and that all my ZA, ZB and ZC are actually equal to ZY, and that I've got a neutral impedance of ZN that I have going down to my ground neutral. From this figure, I can deduce that my VAG is going to be equal to my ZYIA plus my ZNIN. Okay, now if I take my IN, I know that I can rewrite it as in IA plus IB plus IC. So therefore, I can end up with an equivalent equation of, in brackets, ZY plus ZN times IA plus ZNIB and ZNIC. I can do the same for my VBG and again for my VCG for the same star node network. So coming from the previous slide, I can now put here my phase currents in terms of my sequence currents, and that my IN being IA, IB, and IC can be equal to 3IO, all right? And this you can get from my symmetrical components lesson, where I was showing you if you add all of those currents together, what you get with your alphas and your alpha squared. Then my Vn will be equal to 3Zn I naught. Then that can make me have my VAG, to simply write it as VAN plus Vn. Okay, so and on the diagram you can see my VAG and the VAN and the Vn, and that simply is my ZYIA and ZNIN. Whereas in the previous slide, I had taken that IN and written it in the IAIBIC format. Now I simply replace it with the 3IO. Then I will be now able to work out what my VA naught is, my VA1 and my VA2, having looked at what my VAG is. Then we are just going to do a quick example before we move on to the other one, where you've got exactly the star connected load that we're looking at, and they give us the values for my IA, IB, and my IC that you have in here. Then they say we must find our symmetrical components. All right, so I go to my I, and you can see that my IO is going to be equal to a third into IA plus IB plus IC. Then my I1 will simply be a third into that formula that you see on the side there, which I get an answer, and my I2 similarly. So therefore, I know that my IN is the IA, IB, and IC together, which really is just 3 times my IO. And I can just go to my IO and multiply that by 3 and get my answer. Whereas I also could have added those 3 things together to get my answer. It just proves that this actually works as is. We then move off to our delta connected loads, and here we will now have 3 voltages that we introduce, VAB, VBC, and VCA, which are across my delta loads into the delta circuit. So if I'm adding the 3 voltages together, I will get that my Z delta into IAB, IBC, and ICA. If I want my zero sequence component of my VAB and BC and CA, I then can do them in terms of VABO. And that of IAB, IBC, and ICA, I can also do them in terms of IABO. So we can rewrite my VABO to be equal to the Z delta IABO. So therefore, I can be able to write out that my VAB plus VBC plus VCA will simply give me my VA minus VB plus my VB minus VC, and then for VCA is my VC minus VA. And from that, we can find that VABO and IABO are going to equate to 0. Hence, in our delta connected loads with no mutual coupling, we know that we are not going to have a zero sequence circulating current. Why? Because there is no neutral point or star point in the system. Then we look at what we call a series impedance type of network. And what it basically says is that you've got a two bus system. So you'll have a bus 1 and a bus 2. And they've simply named your bus 1 phases as ABC and your bus 2 phases as A apostrophe, B apostrophe, and C apostrophe. Then the self-impedances in each of the phases can be denoted as ZAA, ZBB, and ZCC. So that is moving from bus A to bus B. So in general, the series network may also have mutual impedances between your phases. So you can have impedances between your A, B, and C network and your A apostrophe, B apostrophe, and C apostrophe. So at the bottom of it, they have written it so that we can see if we have got that combination as well. That now my VA minus my V apostrophe N, so that's bus 1 minus my bus 2 voltage, will actually be giving me a voltage called my VA A apostrophe. And that will be simply ZAA multiplied by IA plus ZAB multiplied by IB plus ZAC multiplied by IC. So my ZAA in this case are equal to my ZBB and ZCC, and ZAB and ZAC and ZBC are also all equal. So you can already see that I will have my ZO being then ZAA times plus 2ZAB, and my Z1 and Z2 equals to ZAA minus ZAB. Then we move on to three-phase lines. So in this section, you can see that I've got an ABC phases on my three-phase line. We can assume that this is a transmission network that we have in the system, where we know that our impedances are inclusive of your resistances and inductive reactances. I introduced something called a ZP, which has got that formula in it, and a ZM, which has got that formula in it. Now, when we're talking about the D's in there, we're looking at your distances between your phases. So our R is the conductor, which is your AC resistance, which is ohms per kilometer. Our DC, that is the geometric radius of a single conductor. And our big D is the spacing between your parallel conductors. Then you've got your frequency of your system, and the last one, which is your DE, being your equivalent spacing of the earth return path. So in this case, I will know that my Z1 being equal to Z2 will actually give me ZP minus ZM. And my Z naught will be ZP plus 2 times my ZM. Then I can be able to work out what my IA for that system would be, and thus I can work out what my ZE for the system will then be. Similarly, my IB would equal to negative IC, which I can see as that formula in B. Then we move off to rotating networks, okay, which is usually our machines that you have, such as your generators. So in my generator, it's similar to what we had seen before when we were looking at your connected loads that I've got a star point in it. And then on the other side, you can see that I've got the motors as well. So that also follows almost a similar type of sequence that we had previously. I just want you to note that on both cases, be it a generator or a motor, when we're talking about the zero sequence network, you must always remember the 3 multiplied by your ground resistance or ground impedance that you are going to have, okay, whereas all of the others, they take exactly what was on your impedance. Then we look at what we call our three-phase two-winding transformers, and this is what they would give you when you move them into a sequence type of a network. So where you can see that you've got your three phases A, B, and C, and then you've got the Zn going through to your ground. In your schematic for your zero phase sequence, we know that we're going to have the 3 times the Zn, and then that is the one that's going through to ground, and then we're going to have the 3 times the smaller Zn, which is really looking at your 3 phases that you have in the system. Then you go to your positive phase sequence, and you can see that that one would really only be looking at whatever is happening on one of your phases. Then this shows you in the number of connections that you would get what you can be expecting to have written onto your system. So the first ones is your single diagrams, how they would show up. And on the next one is schematically how you could draw this, and then at the bottom of those we split them up into our zero, our positive, and our negative phase sequence. So I want you to again note that on the zero phase sequence you would have those 3 multiplied by the Zn of your ground impedance, and then on the other side is the 3 of just looking at your 3 phases of your impedances. Then if you go down to your positive phase sequences, then there you just have one of your normal impedance, and then one would be your ground impedance. It's 1 plus 1 that you would add into there, as well as your negative phase sequence. Then this is our last slide for this module, and in here I'm showing you all types of zero sequence equivalent circuits for your transformers. So looking at the very first one on our left hand side, if we have a star-star connected network, then how would we draw our zero phase sequence? You can see that I've got there between my A, my B, my C, and my B over there. You can see that I'll have that Z transformer in, but then they will have an open circuit on either side of that transformer type. So your system will be disconnected by default. Then if you have one where one is just got the neutral and the second one is got your neutral connected to your earth point, then you see now the difference from the above one is that where there is that earth point neutral connection, you've got an impedance that you can connect into that part. So that circuit becomes closed and no longer an open circuit. Then you go to the bottom one where you can see that you've got your both transformers are earthed through that point, so it will normally give you that you've got your ZT in there and either side of those is connected, whereas the bottom is open circuited. Then for your star to delta connection, you must just also note how your connection will look on your zero phase sequence. And then on your star delta, your star being earthed, again, how it will look. And then you've got your delta delta scenario, and you can see it just goes right to ground and there's no connection on either side of your buses in there.